All right, so if you were having problem with the differential equation stuff from Tuesday and Wednesday, that will be something that's going to continually come up for the next couple days. So I'm not necessarily terribly worried because the process will be very similar. It should be something that will transpose between what we do over these next couple days and this. What we're going to do is we're going to look at a couple of very specific examples. We're going to look at a model that you've used a lot, exponential growth and exponential decay. We're going to start off with those, and then what will happen is we will, on Monday, translate from exponential growth and decay, which is really cool, really great, except, let's face it, when we think about exponential growth and decay, what type of things do we usually think about? When you think about population of bacteria, what? Okay, bacteria. Really populations in general, we think about exponential growth and decay. Huh? Money. Sometimes we'll talk about exponential growth and decay in terms of money, which would be our money situation. There's a problem, of course, with exponential growth and decay. You can't really talk about population because eventually the population gets too large for the area, and you reach your capacity, population capacity, and then you're stuck. And we're going to talk about how we can actually modify exponential growth and decay today. And on Monday, we're going to talk about how we can actually modify our exponential growth and decay problem to create what's called logistic growth and decay, which fixes our carrying capacity issue. But before we do that, let's go back to exponential growth and decay. You've been talking about exponential growth and decay for a long time. Since Algebra 1, you've talked about exponential growth and decay. Stuff like, hey, I've got a population of 500 people, and the population is increasing by 7% every year. So you're like, okay, so 500 times 1.07 to the t, and you came up with that equation, right? Yeah. And that was beautiful, and it made sense, and it was great. Then pre-cal happened. And then in pre-cal, you got asked the same exact question, except whoever it was that you had for pre-cal went way off into who knows where land, and they wrote some equation like this. Or maybe it was an R. Maybe you heard it, maybe you remember it not as that, but maybe you remember PERT. And trying to figure out what on earth was that, and you were doing the same question that in Algebra 1 made perfect sense, but then suddenly you were forced to find this P and this R value that was a pain in the butt to come up with, and it was really stinking annoying. I apologize, that's my fault. Why? Because that stems directly from an understanding of the calculus side of the problem. So what kind of happened is you get used to playing with the arithmetic and the algebra side of exponential growth and decay before you actually get a chance to see where on earth it comes from. So let's talk about that. Exponential growth and decay is specifically this concept that between different time periods, whatever I'm looking at, population, my money, if I'm looking at stocks or something like that, that would show, if I'm looking at something that's got a percentage increase or a percentage decrease, ideally what happens there is that we get a rate of change that is actually going to be equal to some proportion of itself. For instance, population. Populations start growing faster when the population gets bigger. That's how it works. As you make more people, those people are able to make more people. So, dy dt, all right, come on. So, dy dt is going to equal this constant times this y. And if we were to solve this differential equation, we wind up seeing how that formula falls out by going, okay, well, if I want to solve this, what do I have to do first? Separate the variables. Get dy over y, which is all right. We can do that. Next step in the process, we would integrate both sides. Antiderivative of dy over y is And the antiderivative of k dt is what? We are taking the antiderivative of k, but we're taking k as a constant. We're actually taking the derivative with respect to t. So a constant with the antiderivative with respect to t would create a kt plus c. At this point in time, you look at this equation and wonder what's wrong with us because we've now written about 15 things on the board and we've not written a single number. I'll tell you what, I'll fix that. I'm going to put a number on the board here in just a second. You ready? There you go. Put a number on the board. kt plus c. And we've already talked about this. We know that y equals e to the kt plus c. I can take this e to the kt, separate it with e to the c. And e to the c is really just oh, look. P e to the RT. No. And it came from somewhere now. Now you know why you dislike it as opposed to just disliking it. That's right. The gold formula? No, absolutely not. Actually, you won't be able to answer the questions using the old formula. All right. So a couple things you need to realize from this. First off, as an exponential growth and decay, this will always be true that if I know I have some dy dt or something like that is equal to a proportion, is proportional to itself. So the rate of change is proportional, is equal to itself times k, then we'll always get the ce to the kt. For some of you, you're going to get really good at realizing, oh, okay, you're going to get to about here, and you're going to jump down to here. Some of you are going to set up this problem and immediately jump into that. Because after you've seen the formula about 5 or 6 times and you've derived it 5 or 6 times, you get really tired of writing down all the steps. Right? Other things I want to know. We're always going to look at situations when y is positive. Because we really don't want to deal with exponential growth and decay when y is negative, because then things start working backwards and it's not very fun. Okay? So y is always going to be positive, which means if y is always going to be positive for our problems, that means c is also always positive. All right? Part 2, there is a growth and decay. Which variable determines whether there's growth or decay? K. When is there growth? K is positive. When is there decay? K is negative, which is actually all stated in the text underneath this particular box. Dang it. So for those of you that forgot that conversation, it's already there. So let's look at our first example. We've got the rate of change of y is proportional to y. That is going to be that's going to be your big ticket right there. As soon as you see the rate of change of something is proportional to itself, that's a pretty good sign that, hey, we've got exponential growth or decay. It says when t equals 0, y equals 2, and when t equals 4, y equals 4. So those of you who are trying to figure out the r issue, what's the problem with that? How on earth do you find a rate? I'm not going to give you a percentage. You've got to figure it out. Oh, dang, that's mean. All right? So, what is the value of y when t is equal to 3? That is all this question is asking, is we just need to find y when t is equal to 3. All right, it's a number bigger than 4. We're good. No, not really. Sorry. It doesn't work that way. Let's go ahead and move through the problem. So, first thing I'm going to write, if this is a free response, I want them to know that I understand that the rate of y is proportional to y. I want to write that down. The rate of y, dy dt, is proportional to y. Proportional means some constant times the y. Yeah, so what it's saying is that let's say for some reason I have a set of t and a set of y values. All right? And if I compare this y value to this y value, this y2 divided by y1 will equal some k. That this y2 divided by y1 will equal k. Yeah, so it's like there's a multiple across all of these. And it's actually, I have to double check and make sure that I'm not off a little bit on that because it's a rate of change. So it's actually, the other part that's hard is that that's an instantaneous rate of change. So for those of you who remember, you had, when you were going through interest specifically, you remember where you started talking about things like compounded quarterly, compounded annually. Then, of course, you got to the really stupid one, compounded continuously. And they said because compounded continuously means it's basically compounded an infinite number of times. Remember hearing something stupid like that? Can I compound something an infinite number of times? No, but what are they doing? Compounded continuously just means that I'm not looking at a dy, I'm not looking at a delta y over delta t, I'm looking at a dy over dt, and I'm looking at that situation. And that's what they're talking about with that type of question. Woohoo! Calculus! It's always fun when you learn that like half of what you've actually learned all stems from calculus, even though you don't actually know any of the calculus. Well, because you got to come up with some application. All right, I'm going to go through my whole thing I'm going to write as I am going to write out this separation of variables. Again, I want to prove to the reader that I know what I'm talking about. I'm going to go ahead, I'm going to say natural log of the absolute value of y is kt plus c, and then I'm going to immediately jump to y is ce to the kt. This, when you take the antiderivative of kt, if I take the antiderivative of k dt, remember that k is a constant, so that's technically k times dt. And if that's a little off, that's 1 dt. Right? Oh, the question, so for those of you who are watching the video, the question was, where did the t come from in kt? I should probably say what the question is. Because otherwise you watch the video and you're going, why is he doing this? All right? So yeah, if you've written this, you should probably erase it right now. Anyways, so I can pull this out and you can see, well, this is 1 times t to the 0 type deal. So when I take the antiderivative of 1, I just get t. Cool. All right, so I'm here. Awesome. Now what? Where do you go? No. Not for at least another 30 minutes. You have to find c. That would be the ideal thing. How do I find c? I've got two sets of things. I've got when t is 0, y is 2, and when t is 2, y is 4. Which one do you probably use first? Probably the first one, because when I get a 0, everything starts canceling each other out. We like 0. 0 is good, so let's use t is equal to 0. When t is equal to 0, I know that I have y, which is 2, is equal to ce to the k times 0. Well, k times 0 is 0, and e to the 0 is 1. Therefore, c is fantastic. We know what c is. Now what? Do the other one. I need to look at when t is equal to 2. I know that 4 is equal to c, but I know what c is now. 2 e to the, what is that, 2k? Cool, that looks good. I'm going to divide by 2. 4 divided by 2 is 2e to the 2k. I don't like the e, so I've got the natural log of 2 is 2k. By the way, I didn't put absolute value. Why did I not put absolute value? It's already positive. Don't waste ink on that. Lead, whatever you're using, as long as it's not blood. 1/2 natural log of 2 is k. What is that as a decimal? I don't really care. Y is equal to 2e to the 1/2 natural log of 2 times t. It's a terrible equation. This is miserable. This is bad stuff. Bad mojo. Question asks, because we're not done with the question, it didn't say just find y, it asked what's y when t is 3? You can either write that as 2e to 2e 3 halves the natural log 2, or 2e natural log of 2 to the 3 halves. I don't care which one you do. Pick one. All right? You do need to be able to translate between the two because you need to understand that multiple choice, I can write it however I want, because actually, if you get it down to this form right here, you actually find out that y actually turns out to be 2 to the 5 halves. So you do actually get a semi-clean number. That's fun. You take e to the natural log, you get 2 to the 3 halves. And 2 times 2 to the 3 halves is 2 to the 5 halves. Luckily, they should not ask you to go that far because at that point in time, what am I really testing you on? Your ability to manipulate exponentials and logs. And while I can test you on that a little, I do not have to test you on that often. Yeah, there's a certain point where it just gets foolish. Questions? You're like, they're not terrible. You start looking for some patterns. For instance, I start looking at the idea that as long as I get a t equals 0, what's always going to happen to e to the kt? It's going to go to 1, which means if I have a t equals 0, my y should give me my c value. So I start looking for those little patterns and those little things. And is it illegal to just say c equals that? Absolutely not. That's good mathematics. You don't have to show me all of that. The things that I do need to see is, do you know your calculus? I don't know about that, but you know. All right. That wasn't bad. We got this. So let's mess with it now. I wonder why. Example 2, the rate of change of v is proportional to v. Again, what is the thing that tells you that this is an exponential growth and decay? The thing is right now it seems dumb that I'm asking that question, but let's face it, what's going to happen is that this is eventually going to be cycled into all those beautiful and lovely questions, and suddenly it's not, oh, this is that type of question that's lovingly encapsulated in the exponential growth and decay. You're going to have to identify that. So you need to know that this is the key phrase, the key statement inside any exponential growth and decay problem. All right? So mathematically, that says dv dt is kv. All right. When t equals 0, v equals 20,000. When t equals 4, v equals 12,500. What is the value of v when t is equal to 6? Oh my gosh, what the heck? I don't even know what the context of this is, but sure, why not? Sounds like fun. Could be volume. I thought it was voltage. Sounds like a voltage question with numbers like that. Remember, it's not the voltage that kills you, it's the amperage. Volume could be. So, now what do we do? Separation of variables, yeah, that's right. dv over v is equal to k dt. I find out that this is, of course, the natural log of v equals kt plus c. V better be c e to the kt, because, hey, it's going to be the same thing every problem we do. There will be zero change. All right, so we got that. Now what? When t equals 0, we know that c should equal. Make sure I got that. So now we need to evaluate k, right? Yes. So I got t is equal to 4. So I've got 12,500 equals 20,000 e to the 4k. By the way, this is an exponential growth or an exponential decay question. What do you expect? Expect growth? Yeah, I went from 20,000 to 12,500. I better be decaying, right? Just using logic, I better get a negative number out of this, shouldn't we? Let's do it. 12,500 divided by 20,000. Drop off the zeros, and 125 divided by 200, divide them both by 25, that's 5/8, equals e to the 4k. So k has to equal 1/4 the natural log of 5/8. K is supposed to be what type of a number? That doesn't look like a negative. I don't see a negative in that at all. Is it? 1/4 of the natural log of 5/8. I want a negative value out of that. So, natural log of anything less than 1, but greater than 0, because remember, we can't be 0 or negative in a natural log, right? We want to remember that the natural log of a value from 0 to 1 is a negative. So do I have a negative k?
Yes.
Sure. What is it as a decimal? I don't know. I don't care. Problem says, what is v when t is equal to 6? So if v equals 20,000 e to the 1/4 natural log of 5/8 times t, then v at 6 is 20,000 e to the 3/2 natural log of 5/8. What is that number? I don't know. But I bet you it's smaller than 12,500.
Yes.
Questions? Hold up. Say it one more time. Yeah, that was where I was talking about that C, because if we were to have actually written that, we would have gotten 20,000 equals CE to the 0, which turns into a 1. So then you get C as 20,000. And that should always happen because K is just a constant. So when my T is 0, K times T has to be... Yes, on these questions you should be getting some zero number. Otherwise, solving for C is terrible. Because you'd actually have to use. The only time that I won't give you an initial condition is if I wouldn't necessarily need to know all of the pieces. So there could be a situation where that happens, but that should not be too big of a deal. So, let's talk about puppies. I knew there was something wrong with you. We've got a puppy. It weighs 2 pounds when it was born. It weighs 3.5 pounds 2 months later. It's a very tiny puppy. If the weight of the puppy during its first 6 months is increasing at a rate proportional to its weight, then how much will the puppy weigh when it is 3 months old? Clearly, this is an exponential growth and decay problem.
Yes.
How do I know that in the context of the problem?
The weight of the puppy during its first 6 months is increasing.
Well, that would be true. You really do want to know that the weight is proportional to the weight. So we want to make sure that the weight of the puppy is proportional to the weight. It is. So we know we've got a dW dt is a kW problem. So I know that. Separate natural log, and eventually, after you've done a whole bunch of stuff, what do you do? I would like you, go ahead and do it. While you're doing that, I will pass out the take-home test. All right. I'll do the hard one. Huh? Does T has to be what? No, absolutely not. If you look, it actually talks about the weight of the puppy in the first 6 months. So we're doing this in terms of months. So I'm hoping you got, at some point in time, your K being 1/2 the natural log of 3.5 over 2. 7/4 would be cool too, but 3.5 over 2 is perfectly fine for me. So then the question, so then after you've solved through everything, you should have got y is equal to 2e to the 1/2 natural log of 3.5 halves times t. And then you need to evaluate y when t is equal to 3, which happens to be, because clearly we know that from our simple abilities. That particular question, absolutely. There would be no way I would ask you to evaluate that in your head. That isn't going to happen. I may be extreme, but I'm no fool when it comes to that. I had no clue what that number was, nor do I expect you to know what that number is. All right? So what about example 4? I love this one. Population y grows according to the equation dy dt equals ky. So what does that tell us right off the top? Exponential growth or decay. So I know, again, that I'm going to get some y is equal to ce to the kt. Where k is going to be a constant and t is measured in years. If the population doubles every 10 years, then the value of k is. That's all they give me. The population doubles every 10 years. So how are you going to do it? I know what country. That's right. You just have to look up the... I'm sorry, what country is this that we're utilizing now? Nope, you actually have enough information to solve for K. You have a couple ways. What are you thinking? I'm interested to see how you would attack this question. Okay, we would have t equals 10 and t equals 0. I like that. So when t equals 10, we need to come up with what a y would equal. And when t equals 0, you got to come up with what y would equal. Because you really don't have an initial condition yet, you just got t equals 10 and t equals 0. Sure. You could put 2y and y. We'd have a population of y when we started. I probably would not do y's just because they're the same thing. I'd pick a separate variable. So personally, I would pick something like c and 2c, p and 2p. I don't care which ones you pick. Does that make sense? That we have some initial value and then we'd have some value doubled, right? All right. So now what do we do? I know from this piece of information, I know what this c would be then. That would be this piece right here, right? So I know that I can look at 2c is equal to ce to the 10k. And this is really nice. Why? So what am I really looking for? Well, I know the answer better not be D. And I know that the answer better not be E, because how on earth do I have a 3 and a 5 if I've got natural log of 2, which is clearly less than E, so it should be less than 1, right? So I have a number smaller than 1, and I want a tenth of a number smaller than 1. So I'm going to have a decimal point that I'm then going to divide by 10. That's right, we just did it without a calculator. Good old logic. Or, you know, this question would have been on the calculator test anyways, but... What did you do?
Because it said it was double, so I was like, all right, I'm going to put 4 as the constant.
Right, no, so you, instead of doing C and 2C, you did 2 and 4? Yeah. That's beautiful. Well, no, I mean, does that make sense? Does Oz's version of, instead of doing C and 2C, does that make sense? Okay, well, we'll just pick 2 and 4. That works beautifully. Absolutely. Huh? 1 and 2 would be a fit. And if you think about it, every time, no matter what two numbers you pick, when I do the 10, the t equals 10 divided by the t equals 0, no matter what I do, what am I going to get? I'm going to get 2. So it doesn't, I mean, you know, you want to do 20 billion and 10 billion? Be my guest. Because no matter what you do, you're going to get 2. Fantastic. Nicely done, folks. All right, so here's what you got. You got 1 homework question and a take-home test. Monday, we introduce logistic growth. Tuesday, we CBA. Wednesday, we continue logistic growth because it's an interesting and really important topic. Wednesday, we do something else that has to deal with math. I can't remember what we're doing Thursday next week. That's a little less than a week away. I can't go that far out. Friday, you have off. Monday, you'll have off. Tuesday and Wednesday after that, I'll be here, and then Thursday and Friday, I'll be gone. So, huh? I will. No, we can't have Miss Bruce because she's busy. So. She lives in Dallas. So there we go.